We're going to start lecture 5 now, which is going to be a new block of material on a new type of generative modeling family called latent variable models. And specifically, we're going to see one really important type of generative models called the variational autoencoder. Let's now do a quick recap of what we've seen so far in the first few lectures. So remember that this is our task, or this figure illustrates the task that we're trying to perform, which is generative modeling. And the way we define generative modeling is that we're trying to build a generative model of some kind of high-dimensional object, such as images in this case. The way we define a model is via a probability distribution. So for us, a model is always a probability distribution. And instead of specifying this model by hand, we learn it from data from a large data set of images, such as here we have images of cats and dogs. And our approach involves 3 components. First, we have to specify a modeling family. This is what's represented by the green blob here. That's the set of all the probabilities that we could learn. And then we choose a modeling family within this class, and we choose it to approximate a data distribution, the true data distribution. We're assuming these images are coming from the data distribution. We define an objective over probabilities, and we try to find the best probability in that class. Once we have learned this model, we can do a few interesting tasks. One thing that we can do is obviously generation. Once we have a probability, we can sample more images, or we can sample text from that model if it's text. We can also do density estimation. In all the previous models we've seen, we can always compute P of X, so we know whether a certain new image looks like our data set or does not look like our data set. This could potentially be used for something like anomaly or outlier detection. And then another task to which I alluded to in the very first lecture, but we haven't looked at yet we haven't looked at it in a lot of detail yet. This is the task of representation learning. If we have a big data set of images, we would like to learn a model such that later when we inspect the model, we can discover something new about this data. So you can think of it as a form of unsupervised learning where you discover something interesting about the data. And so far, all of our lectures have focused on the 2 applications, generation and density estimation. We saw how we can do these tasks with autoregressive models. In this lecture and in the next lecture, and also we're gonna revisit this topic throughout the course, but for the next few lectures, we're going to now switch gears and look at this 3rd task of representation learning, which I think is equally important, and it's a central task in generative modeling. We're going to look at how we can solve this task, and we're going to have to use a different set of models from the ones we introduced in the first few lectures. So before I introduce anything new, let's again remind ourselves what are the. Let's look again at the models we defined in the first 4 lectures. We mostly looked at these families of autoregressive models. And the idea of an autoregressive model is that you have a probability distribution over some high-dimensional vector x, which could represent our image, and then each component of x could be a pixel. For any distribution, we can apply this formula, which is the chain rule of probability. We can write it as a product of factors. And then the idea of a neural autoregressive model is that we approximate each of these factors by a model that's parameterized by a neural net. And in the context of images, you can think of this model as being a neural net which predicts a pixel given the previous pixels. Or if this is a model over text, it predicts the next word given all the previous words. And if we can predict the next word, then we can solve the tasks that we talked about. We can perform density estimation. We can evaluate the likelihood of the data by simply looking at the probability of each pixel conditioned on all the previous pixels. So we literally just apply this formula, and we evaluate this formula on the images using our model that's parameterizing P. And because we can evaluate likelihood, we can also directly use this objective for optimization. We can learn this. We can learn the parameters of an autoregressive model by maximizing the probability of the data. This is the principle of maximum likelihood, which was the focus of the previous lecture. And once we have defined this model, then we can sample from it by generating each pixel or each word or each component of X sequentially. So we start by picking the first component at random, then we generate the second component from the probability that we have for that component given the first component. Then given the first two components, we predict the third component, we generate a sample from that, and so on until we get a full image. So here, sampling is possible, but I would say one of the cons of a regressive model is that this sampling process tends to be sequential and therefore slow. If you have a high-dimensional image, then let's say this image has tens or hundreds of thousands or maybe even millions of pixels, then you have to have a loop that runs a million times to generate pixels one at a time, and this can be slow. This is especially slow for models over very high-dimensional data, like high-fidelity audio. If you wanted to generate from a model like WaveNet, it's very slow. Even though it gives you good samples, you get really the samples are high quality, but the sampling tends to be slow. And we're gonna revisit this topic in a few lectures from now, and we're gonna see ways of accelerating, speeding up sampling in autoregressive models, but that's gonna be a topic for a little bit later. And then another problem with these autoregressive models is that they're very good at sampling, they're very good at evaluating the likelihood, but they don't really solve this other problem that I mentioned at the beginning. They don't naturally let you learn some interesting new structure about some interesting new, they don't provide any new insights about the data. Let's say you wanted to discover some clusters in the data, or you wanted to find patterns in the data in an unsupervised way. This is not really something that our regressive models are naturally suited for. And so the whole premise of this lecture and the next lecture is going to be to try to address this limitation of regressive models, the fact that they can't do representational learning. We're going to introduce a new type of generative model called latent variable models, and specifically variational autoencoders are going to be a special type of latent variable models. And then we're gonna start by defining this model family in this lecture, and then we're gonna look at learning at the end of this lecture and mostly in the next lecture. Okay, so that's the plan. That's the recap and a plan. And of course, the motivating task here is representational learning. So we should talk a little bit about what is representational learning. As an example, imagine a data set like this one that we would like to model and that we would like to do representational learning on. Clearly, there's a lot of patterns. So this is a data set of human faces, and there's a lot of structure in this data. There's different kinds of humans, but there's similarities and differences between these humans. So there's individuals here of different, they have a different gender, different eye color, skin color, different age. Some of them are wearing glasses. Some of them have longer hair, different hair color. So there's a lot of factors of variation in this data set. And ideally, we would like our algorithms to be able to capture these factors of variation. This could be useful if we wanted to then later generate objects with a certain set of properties. If we wanted to manipulate images, it could be useful to automatically discover what the key factors of variation are. But more generally, this is also an interesting scientific problem. If we are able to discover in an automated way what are the main factors of variation in the data, then it feels like we're learning something about what the data is, and it seems like our algorithm is providing some insights. It is actually discovering some important concepts here in an automated way. This seems like a path towards a system that is behaving intelligently. And of course, there are again some practical applications, again, we could discover some interesting new facts about this data. Maybe there's a certain distribution of different types of humans in this data set that we weren't aware of. So you could also do all sorts of practical applications of unsupervised learning. And it's also an interesting scientific question to try to understand the factors of variation in this data. So how might we learn these factors of variation? And what does it even mean to learn factors of variation? The first thing to note is that these, what I mean, the examples of structure and variation that I just gave, this information is not present in the data set. There's no labels that indicate that a person is male or female or old or young or wearing glasses, not wearing glasses. So this structure is latent. It's there, but it's not explicitly written down for us. And so, therefore, we will apply this idea of latent variable modeling to learn these factors from data. And in particular, we're going to model these factors as an additional set of variables, which I'm going to denote by z, right? So before we used the variable x to denote the object, or in this case, the image, which is visible. Now we're going to add another set of variables z, which will represent that unknown, these unknown characteristics of these unobserved characteristics of the data. And we're going to learn a probability distribution over both x and z jointly. So that's going to be our strategy. Now, a little bit more formally, what is a latent variable model? We've seen this in, or I think some of you should have seen this in some machine learning classes that you took earlier. But at a high level, you can think of a latent variable model as a probability distribution over, as I said, two sets of variables, x and z. X is our image, z is some variable that we're going to add, which is not in our data set. Right, x are the observed objects, and then the z are some interesting facts about x. Right, x is one data point, z is its latent representation, and z has some information that's interesting to us, but we don't observe it. So we're going to use some unsupervised learning techniques to discover it. And the idea is that we want to learn a joint distribution over x and z. So what could be an example of a distribution over x and z? Here is, this is a toy example. This is not the complete definition of a distribution, but you can think of, in this data set of images, you can think of there being some interesting characteristics about the data, such as gender of the person, their hair color, the pose, the way it's looking at the camera, their ethnicity. There could be some dependencies between these variables. So probably the ethnicity of the person influences their eye color and their hair color. And then these latent variables, in some way, determine the image x. So the image x is sampled from a distribution that's conditioned on these latent variables. Okay, and so if we could learn a distribution over both these characteristics and the image, then we could ask the model for, oh, okay, given that I have an image x, what are the characteristics z that are most likely given this image? So we could compute the formula for p of z given x, and then p of z given x identifies these latent characteristics. But again, as you can imagine, this is hard. First of all, well, again, z is not observed, so we have to use some clever unsupervised learning. Because z is unobserved, these unsupervised learning algorithms are often intractable. They're not, they're computationally hard. They require various kinds of computational approximations. A lot of what we're going to see in the next few lectures are approximate inference algorithms for these methods. And then the other challenge is that it's unclear how to even specify this model. First of all, p of x given z it's hard to specify by hand what is the shape of a distribution over human faces given their gender or eye color or hair color or pose. X is just a large matrix of pixels, and here we have some categorical variables. How do we even define this mapping? So to address this challenge, we're going to use again the machinery of deep learning. Instead of trying to specify this x given z by hand, we're going to learn it from data. We're going to use a neural net to specify what x given z is. We're going to give the model a lot of data, and we're going to hope that it discovers this mapping on its own. So that's one challenge. And then another challenge is that even specifying the z is also unclear. It's not obvious how to specify z by hand. So here we have a data set of images. We could guess what the latent factors of variation might be, but these might not be the best types of the best factors of variation. So here, for example, we're not specifying age. Maybe age is a really important one, but we forgot to include it. Or maybe we have some data set maybe we have some medical data set, or maybe we have MRI scans, and who knows what are the right factors of variation to include in MRI scans. So even specifying z itself is challenging. We're not sure what the right model for z is. And again, our strategy is going to be to use neural networks to learn, we're going to use neural networks in a way that doesn't specify really what z should be, and we're going to let the model discover that on its own. So specifically, what do I mean by that? When we talk about representation learning in this class, we're not really talking about these kinds of structured categorical variables. We're going to be working with another type of representation, which is called a distributed or continuous representation. And what this means is that we're going to map images into some vector, some continuous vector of numbers that doesn't necessarily have any meaning, but and then the mapping between z and x is going to be completely determined. It will be completely learned by the algorithm from data. It will be parameterized by some flexible and expressive neural net. But z will still be a useful representation in the sense that the model will learn to map similar images x to similar z. So even though we're never, well, in some cases we might, but this is more of a kind of this is not something that works reliably. Most often we will not be able to go and inspect each component of z and try to understand, is this component responsible for their age or their gender or their pose. Usually all of these factors will be in some way will be mapped in some often nonlinear way into a vector z, but similar images will fall in similar regions of the space of z. And therefore, we're going to be able to do interesting things like interpolate between images, manipulate the vector z to obtain images with certain properties. We're going to be able to visualize the z and observe interesting patterns in that latent space. The data might form interesting clusters in this continuous distributed latent space, and interpreting these clusters will give us useful insights. So yeah, this continuous latent representation will still be useful. So this is an example of how this continuous latent representation could be useful. Here, what you see is the result of running a certain latent variable this is the result of applying a latent variable generative model to a data set of handwritten digits. Remember, we saw this data set in several of our earlier lectures. So we learned this model, and in that model, we asked, so this was a model over the images x and an additional two-dimensional latent variable z. And after we learn the model, given each x in our data set, we can ask, what is the most likely z? And so for each x, we get a two-dimensional representation of that image. And what we have on this figure is a plot that shows that visualizes these two-dimensional representations. So each point here in this 2D plane, it's an image, and its coordinates are given to us by the 2D representation z that the model has computed for x. Okay, so here the model has learned to map images into a two-dimensional latent space. And what you see here is that the model has learned to discover, the model has discovered interesting structure in this data. There's obviously clusters here. Yeah, there's some clusters. So when we trained this model, we didn't give it any labels for what the digits are. But once we have trained the model, we can go and inspect what it has learned by coloring each point according to its label. So here we've colored all of the 2s in red, all of the 1s are green, etc. And we see that the model, in an unsupervised way, has learned to separate the 2s from the 1s, from the 6s. So it has learned automatically on its own the concept of a digit, and it has mapped the digits to, it has mapped different digits to different parts of the space. Different digits form different clusters. So here it has learned automatically the concept of a digit. And furthermore, it has even learned additional structure that was not present in our data set. If you look at the 2s, there's actually two different ways of writing the digit 2 in the real data. One of these ways uses a loop in the tail of the 2, and the other one doesn't. And it has learned to separate them out automatically. And similarly, there are two different ways of writing a 1. You can write it as a straight bar, or you can write it as a slanted line. And it has also learned to map these digits to different clusters. So this is the kinds of things that you could discover using a distributed latent representation that will be learned by the kinds of algorithms that we're going to see in the next few lectures. And then another interesting thing that you can do is, once you can map objects to a latent space, you can manipulate these latent representations in interesting ways. This is one example where we applied a similar algorithm to human faces. And once we have those latent representations, we can take a new image, we can encode it into its latent code, we can map it to its latent vector, and then we can generate similar images to that initial image. So if we take a smiling woman, we map it, so our smiling woman, this set of pixels, that's the X, we map it to some Z, then we can generate images from similar Z, which gives us more images of smiling women. We can also then take this vector for a smiling woman, take the representation, take the encoded vector for a neutral woman, subtract that away, and add in the representation, add in the vector for a neutral man. And that gives us some other vector. And if we sample new images from that vector, we get images of a smiling man. So essentially, we took the concept of a woman, we removed it, we removed the part of it that is a woman, we added the concept of a man, but the concept of smiling was preserved. So now we can generate images of a smiling man. And these kinds of manipulations can often be done in various types of latent variable models. Okay. And again, all of this is learned from data. And also, just to be clear, when I have minus, plus, these are operations in vector space. So we're taking some vector, we're subtracting another p-dimensional vector, and we're adding back another vector. And then we generate from that Z, we generate images with that representation. And that's how we get the image on the right. So these are cool things that you can do with latent variable models. Hopefully, this was a bit of motivation that shows why this is interesting and why this is important. Next, let's look at some examples of deep and also shallow latent variable models. Okay, so let's look at a few examples of how a latent variable model might look like. The simplest latent variable model that I can think of, or one of the simplest that I can think of, is a mixture of Gaussians. That's something that you should have seen before in an earlier machine learning course. So you can think of a mixture of Gaussians as being a latent variable model with two types of variables, x and z. And z is going to be a categorical variable that takes its value in among one of k categories. So here, k equals 3. And k is the number of clusters, the number of Gaussians in our mixture. So this is how z is. And then x given z is going to be a Gaussian with a mean and a variance that depend on the variable z. Okay, so for each value of z, and there are k possible values, x condition on that z is a Gaussian, and that Gaussian has parameters. It has a mean and a variance, and that mean and the variance are different for every assignment to z. Okay. So this is this distribution assumes that the data is a mixture of k Gaussians, where the probability of each Gaussian is given to us by p of z, and then p of x given z is the probability of the data, given that we are coming from the Gaussian. We can visualize it as follows. Here we have 3 Gaussians. These ellipses are visualizing the shape of the Gaussian in 2 dimensions. And if we were to sample from this data, we could first sample a value of z that's choosing a cluster from our prior distribution over clusters, and then we can sample an x from that cluster. So here we might choose 3, and then we would sample something from 3, and then we could choose 2. We would sample something from 2, and this would give us, this sampling procedure would give us a distribution of points in 2D space that look like they're coming from a mixture of Gaussians. So here is an example of how this might look like with 2 Gaussians. So this is actually a real data set. This is the data set that shows the duration of an eruption and then the time between 2 consecutive eruptions of a geyser in Yellowstone National Park. But it doesn't matter. The specific definition of what this data is not that important. The key idea here is that this is how a data that is approximately coming from a mixture of Gaussians looks like. And there are 2 components here, clearly, and we could model this distribution using the probability distribution I showed on my earlier slide. So if we were to fit a single Gaussian, this wouldn't be a good fit. Clearly, this doesn't look like a real Gaussian, because in the middle of it, where we should have the most probability, there's barely any data points. So this is not a great fit for a Gaussian, clearly. But a much better fit would be a mixture of 2 Gaussians. So there would be a Gaussian component at the top and a Gaussian component at the bottom. The rightmost figure shows how a mixture of Gaussians can be a good fit. And it's an example of how data coming from a mixture of Gaussians would look like. And again, we could use mixtures of Gaussians for various tasks. We could do generation in the way that I just described. We sample from z, then we sample x given z. And we can also do representation learning. There is a formula that we have seen in earlier machine learning classes for the probability of z given x. In the context of a mixture of Gaussians, the probability of z given x is a probability that is the p of z given x tells us from which cluster is x most likely to have originated. And so you can think of this posterior as doing a crude form of representation learning. Here, the latent representation is just one of k possible values, and p of z given x predicts what that value might be, and it just happens to be that z happens to be one of a finite number of options. It happens to be a scalar. It happens to be one of these k categorical options. Okay. And then the other interesting observation here is that by having a mixture of Gaussians as opposed to a single Gaussian, we can fit more complicated distributions. So this should be obvious. Clearly, this distribution is not a good fit for a single Gaussian, but by adding more components, we can get a better fit. That's a simple observation to which I will come back in a few moments. Okay, so this was an example of a very simple model. what would be an example of a more interesting model? And in particular, can we extend this idea of a mixture of Gaussians to something more complicated that starts to use neural networks in the ways that I alluded to earlier? And the way that this would look like is, might be something like this. So a Gaussian mixture model is a mixture of a finite number of Gaussians. There's 3 Gaussians, 5 Gaussians. What if we extended it to have an infinite number of Gaussians? Can we do this? In some sense, yes, we can. And this is what the following model does, which I'm going to call this model a deep latent Gaussian model. But this is also the model that's used within the variational autoencoder algorithm, which we're going to be deriving over the next few lectures. In this model, again, we have this latent variable structure. So we have to define a prior over Z. We're going to set the prior to be just a Gaussian distribution with a mean of 0 and a unit variance. So I is the identity matrix. And then we also have to define the probability of X given Z. Previously, mu and sigma were a function of a categorical Z. Since we only had a finite number of options for Z, we could just specify, all the possible mu's and sigmas as a table. So for each possible, if I have 3 Gaussians, I just need to specify 3 vectors. Now I have an infinite number of values that Z could take. Z is now a continuous Gaussian variable, but I still want to have some mapping from Z to the mean and the variance of the Gaussian. So one way in which we could do this is to have the mean and the variance be a neural network. It's going to be a neural network that will take as input a vector, Z, and it will output another vector, mu of Z. Mu is going to be the conditional mean of the distribution P of X given Z, where it's conditional on Z. Okay, so here's an example. So remember, we're saying that Z is a d-dimensional vector, X is a d-dimensional vector. Therefore, mu, the mean of X, will also be a d-dimensional vector. And we could make it a neural net as follows. We take the Z, we apply a fully connected layer with a nonlinearity of sigma. A here is a D by P matrix. So now mu of Z is some vector, it's a d-dimensional vector that's a nonlinear function of Z, where A and C are learned parameters. Okay, and if X has 2 components, then the first component will be this, and the second component will be that, and A1 and A2 are just the columns of the matrix. Okay, and similarly for sigma, we typically assume that sigma is diagonal, so sigma also has D parameters that parameterize it, so we can do the same thing, except that the entries of sigma should be positive, so whatever the output is from our other neural net that has parameters B and D, we exponentiate that to make sure they're positive, right? And this is how the matrix will look like as a function of Z. So when we define this math, we get a valid probability distribution over 2 continuous variables, X and Z. Z has some loose and informative prior. It's going to be this continuous vector, which, by the way, Z will be our distributed continuous representation, like what I had in the earlier examples with the digits and the unifaces. This is what Z will be. It will be a continuous vector. And then this continuous vector maps to the parameters of a distribution X given Z. And if we multiply these 2 distributions, we get a valid joint distribution. Its parameterization is complicated. It's some kind of neural net, but it's still a valid distribution. It has parameters A, B, C, D. And we could try to now learn that distribution. Okay? And if we learn the distribution, we're going to be able to perform many tasks. We're going to be able to generate new images. We can sample a Z at random from unit Gaussian, pass it through the neural net, and get a mean and variance over X, sample from that, and get an image for X. And given an X, we could also ask for what is the most likely Z given X, and that's going to be a form of representation learning. Okay, so this is going to be a model which I'm going to call an infinite mixture of Gaussians. or a deep latent Gaussian model. It is like a mixture of Gaussian, but Z is a continuous vector, and therefore the mapping between Z and the parameters of P of X given Z has to be given by some kind of parametric model like a neural net. Okay, so this specifies a distribution, but this distribution is going to be more complicated than the autoregressive models we saw in the earlier lectures. In particular, the fact that we're going to have these latent variables will make things much more complicated. What do I mean by that? So let's say we wanted to learn this kind of model. So this model defines a probability for each image. For each X, there is a P of X. And we saw that anytime we have a P of X, we can maximize it over our data distribution, over our training set. And that's a valid way of learning any model. It's called maximum likelihood learning. So this is a distribution. There is a P of X. We could apply maximum likelihood learning to find the parameters that maximize P of X, or in other words, maximize the distribution of the data. However, this becomes much more complicated because we have this extra variable Z. So the correct formula for P of X is a sum over all the possible Z's. So let's assume for now that Z is discrete, as in a mixture of Gaussians. Okay, so we don't have a formula for P of X. We only have a formula for the joint P of X and Z, right? And this is our formula. When we have P of X and Z, we can always compute it by doing P of Z and then computing P of X given Z. We have a formula for each component, but we don't have a formula for P of X. Therefore, we have to do this sum to get the correct formula for P of X from our earlier, from this other definition. In particular, if P of Z and P of X given Z represent a mixture of Gaussians, then this will be the probability of X. It will be the weighted probability of X under each of K component of the Gaussian. Yeah, that's just the standard definition of the probability under a mixture of Gaussians. We can visualize this objective, and this is what we're doing at the bottom. So the probability of X given Z, it's a weighted sum of Gaussian probabilities. This is why it's called a mixture of Gaussians. The right-hand side here is the mixture of Gaussians. We have K Gaussians. We're computing their probability and taking the weighted average. That's the definition of a mixture. And a mixture of Gaussians looks much more complicated than just a single Gaussian, which is what the figure at the bottom is showing. So here, there's these three bell curves. There's a blue bell curve, there's an orange bell curve, and then there's a green bell curve. Each of them on their own is simple. It looks like a regular bell curve with a single maximum, but their mixture now has this more complicated shape. On one hand, it's good that it has this more complicated shape. It means we can use it to fit more complex distributions. But if we wanted to learn this more complicated shape, now things become more difficult. Now this probability is not concave. It has many kind of local optima, local maxima, minima, saddle points. It has a more complicated shape, and it will be harder to learn. I guess this expressivity comes at a cost. It becomes more challenging to learn this shape. Okay, and in particular, this is why in Gaussian mixture models you have to use methods like expectation maximization and so on. This is just a more complicated problem now. In particular, so if we have a mixture of Gaussians with K components where K is not too large, like 5, 10, this is still tractable. And so we saw algorithms like EM that can solve this problem. But in many of the tasks that we're going to be working with here, Z could be very, very large, or it could even be continuous, right? So first of all, this Z here, if we're working with a continuous vector of Z, then this sum becomes an integral. And now we have to somehow compute an integral, which is going to be potentially more complicated than just computing a sum. And even when z is discrete, computing this sum might be very expensive. Let's say that z is a 30-dimensional latent vector, which is reasonable if our images are 784-dimensional or more. 30 is not such a big dimension for the latent vector. And let's say each component of z is binary. Then this summation would be over 2 to the power 30 terms, which is way more than anything that we can do in a reasonable amount of time. So computing this sum will be in many cases intractable, either because there are too many z's to sum over, or because the z's are continuous and then we'll have an intractable integral. Okay. And because it's hard to compute the log likelihood, it's also going to be hard to compute the gradient, right? This is computing the objective is the forward pass. The backward pass is to compute the gradient. If the forward pass is hard, the backward pass will be equally difficult. And therefore, we're going to have to use approximate methods to learn these distributions. Okay. So how can we have a tractable approximation to this marginal log likelihood objective? Well, we're going to use a strategy that is called variational inference. And in the next few slides, I want to explain what variational inference is at a high level, and then we will complete the picture in the next lecture. So to define what variational inference is, let's start with the following observation. I'm going to do a little bit of math to massage this intractable objective into something that is more tractable. And the first step that I'm going to do here is I'm going to do a little bit of simple algebraic manipulations where I will start with this intractable log likelihood, and I will, here within each term of the summation, I will multiply and divide by some arbitrary function q. So actually, q is going to be a probability distribution. I will just, let's say we have any probability distribution q. If I just divide and multiply by it, that's just 1, so this doesn't change anything. But for now, bear with me for a moment. Let's just do the exercise of here doing this operation, which doesn't change anything. So here in the first equality, nothing changed. But one thing that we can observe about the middle term is that now this looks a little bit like an expectation. I am summing over some number of z's, and each term in the sum is weighted by a probability distribution q of z. So essentially what I have in the middle is the log of an expectation where the expectation is taken with respect to z sampled from q of z. And the term of which I'm taking the expectation is now the ratio of p of x given z to q of z. Okay, so far this is just a bit of algebraic manipulation. The reason why this is interesting is that because we have an expectation, this is starting to look like something that we might potentially approximate using the techniques we saw in the previous lecture. In particular, if we have an expectation, we could maybe try to use Monte Carlo to approximate this intractable expectation with a smaller sum. That would be our hope. However, we have a problem. Here, we don't just have the expectation, we have the log of an expectation. And we can't really flip the expectation and the log. We can't flip two operations. We can't flip the x and a nonlinear operation. A log is nonlinear. So the x of a log doesn't equal the log of an x. If we had the x of a log, then we would be in great shape, because the x of something, we can approximate that using Monte Carlo. That's a technique that we have that could be applied here. But we don't have that. We have something a little bit different. We have the log of an x. So I would like to take this log of an x term and massage it into something which is going to be an approximation to the the other way. I will take I will show that there's actually an interesting connection between the two. And this connection will be based on something called Jensen's inequality. Jensen's inequality is a very famous inequality in mathematics and convex analysis. Let me define what it is here. So recall that we have this. So this is just the same equations as on the earlier slide. I have the log of an x. I'm hoping to flip the x and the log. Well, we know that log is a concave function, and Jensen's inequality tells us that for any concave function, the average, the weighted average of the log of a weighted average is lower bounded by the weighted average of the logs. Okay, so imagine I have two x's, x and x prime, and I want to take some kind of weighted average that's weighted by p. So that's what I have here. P of x plus 1 minus p of x prime, where p is some probability between 0 and 1. So x and x prime, that's like taking their average. That's like interpolating between them. And the log of the interpolation is always going to be greater than the interpolation of the logs. That's what Jensen's inequality tells us. So again, what is Jensen's inequality? It's this idea that the log of the interpolation is greater than the interpolation of the logs. So specifically, if we have an expectation, well, an expectation is just it's just a type of interpolation between different f's, right? And I think the best way to understand why Jensen's inequality is true is to look at this picture. Let's say I have some function f of z, and I'm evaluating it z1 and z2. If I interpolate between f of z and f of z2, then that gives me something that's on the interval between f of z and f of z1, and the value of the log. So here this red line, that's the right-hand side of the inequality. That's what happens if you take log of f of z of 1 and you average it with log of f of z of 2. So the interpolation of the logs will be on the red line, but the log of the interpolation is going to be always above it. So this is why this inequality holds. Okay, so this is Jensen's inequality. And now, as you probably see where I'm going, we can apply Jensen's inequality to our to this term, to the term that I just derived. So here we have the log of the expected value. I told you it's not the same thing as the expected value of the log. It's a little bit different. It's actually a lower bound on the expected value of the log, right? So just to be super precise, we want to apply Jensen's inequality to the term that's at the top on the right. Here in the middle, I have Jensen's inequality. We're gonna let f of z be the ratio of p over q, and then applying Jensen's inequality with this choice of f, we have the following relationship. So the two terms that I had on the other slide that had the inequality, they're not the same, but they're still related because the x of a log is a lower bound on the log of the x. Okay, so they're still related, and this is going to be useful. This is going to be very useful. In fact, this term, which is the x of the log, this has a name. It's actually a very important objective in generative models. It's called the evidence lower bound, or ELBO for short. And although we're never going to be able to, or in most cases, we're not going to be able to optimize the actual marginal likelihood, we will, in many cases, we will almost always be able to optimize, in fact, maximize a lower bound on the objective. And if we can maximize the lower bound, then in some way, we're also maximizing the actual objective. It's as if we're pushing the maximum likelihood, pushing the marginal likelihood from below by pushing the elbow up. So that's going to be our strategy. Instead of optimizing the marginal likelihood itself, we're going to be maximizing this lower bound called the elbow. Okay, and this inequality summarizes what we just showed. The marginal likelihood is lower bounded by this elbow. We can do a little bit of massaging on the elbow. So there's actually two components to the elbow. If I separate out the log, then the elbow is actually is actually this expected, so this sum over Z plus the entropy of Q. Well, that's what you have here on the top. And the idea of the idea of variational inference is, like I said, instead of optimizing log of P of X, we optimize the elbow, and we also optimize it over Q. So remember that in all of these derivations, I never told you what Q is. I just said this is true for any Q, and it's true. You can choose any Q, this will be true. But some Q will be better than others. And as I will show you on the next slide, for certain Q, this lower bound will be tighter than for other Qs. And so the idea of variational inference is that we maximize the lower bound, but we also maximize the lower bound over Q to get something that's as tight as possible on log P of X. So these are the two key ingredients of variational inference. Okay, so I just said that some Qs are better than others. So what makes a good Q? We can find out what is a good Q by doing a bit of a bit of algebra here, a bit of algebraic manipulations. Observe that, well, it's easy to check that the following equality holds. Remember that we defined in the last lecture this concept called the Kale divergence, which is a notion of closeness between distributions. So consider the Kale divergence between Q and P of Z given X. If you just plug in the definition of Kale divergence and work out the terms, this equals precisely to the log probability of X minus this other term, which is just the elbow. Or in other words, if you rearrange the terms, you get that the log probability equals precisely the elbow plus the Kale divergence between Q of Z and P of Z given X. Okay, so here X is just a fixed data point for now. We don't have a data set, we just have a single data point. Given the data point, there are these two well-defined distributions, Q of Z and P of Z given X, and the Kale divergence between Q of Z and P of Z given X is precisely the gap between the elbow and our maximum likelihood objective. So here we've quantified the gap, and also this formula tells us what the ideal Q of Z should be. The ideal Q of Z is precisely P of Z given X. And if we can choose our Q of Z to be that, then the elbow is an exact approximation to our objective. Okay? So that's good. We know what we need to learn. Now, the problem is that P of Z given X is in general intractable. The whole reason why we do these approximations is, so P of Z given X, its formula is P of X given Z divided by P of Z, right? P of X given Z divided by P of X. And that P of X is the same thing, it's the same P of X as here. So it's almost always intractable to compute the true P of Z given X, right? If it was tractable, then we wouldn't need this whole variational inference machinery in the first place, right? If P of Z given X was tractable, we could just use it directly to get what we want in a simpler way. So we're rarely going to be able to set Q to be exactly P of Z given X, except in a few cases like a mixture of Gaussians. And in that case, we get exactly the EM algorithm. So that's a little side note. What does the EM algorithm do? It actually sets Q of Z to be P of Z given X inside the E step. But anyway, that's just a slight side note that I won't talk about, but you can double check that on your own, or you can talk to me later if you want. But in other cases, we're just going to be able to find a Q that's closer to P of Z given X, but not exactly equal to it. Okay, so this is what we're trying to do here. Okay, and so the whole idea of variational inference and learning is to form this lower bound, and then we're going to Well, we're ultimately going to be optimizing theta. We ultimately want to learn what p is, so we ultimately are optimizing over theta. For now, let's assume that theta is fixed, and we just want to find a good objective for it. So what we do here is we'll try to find a good q. Then once we find a good q, so this will be itself an optimization problem. We're going to optimize over a set of q to find one that maximizes the elbow, which means that makes the elbow tight. Once we have finished optimizing for q, we fix it, and then in the next lecture, we're going to show how we can take a step on theta. Once we have taken a step on theta, we will need to recompute q because a different q will be optimal for a different set of theta. And so essentially, we're going to be optimizing this elbow. In the next lecture, we're going to be optimizing the elbow over both theta and q jointly. And by optimizing them jointly, we're going to be hopefully optimizing a tight lower bound on the log likelihood objective. So that's the strategy of variational inference. But for now, for the end of this lecture, I just want to show what it means to find a q when theta is fixed. Okay, let's just say that for now we're in the innermost loop where we want to optimize the elbow. We now have a formula for it, but we have to find a good q. So what does it mean to find a good q? Well, finding a good q involves two tasks. One is representation. We will want to define some parametric family for what q might be. Okay, so anytime we have some kind of optimization task, we have to define the set of things we can optimize over. And in this case, that's q of z given phi with some parameters phi. So we have to define this parametric form. And then we're going to perform this optimization procedure in some way that I'm going to talk about later. So these are the two steps for finding a tight elbow. And again, once we have a good tight elbow and we have a good phi star, then we can start optimizing over theta, which is what we're going to do in the next lecture. So that's our strategy. And now I just want to end with two slides which show two examples of what this optimization problem might look like. So yeah, what might be an example of this procedure? Here's one simple procedure where we're trying to apply variational inference to try to fit an approximate posterior p of z given x, which is this distribution given in blue. Right here, I have three distributions in this figure. There are two Gaussian distributions, the green and the yellow, and then there's this non-Gaussian distribution in blue. And let's say that this distribution in blue is that true posterior p of z given x that I want to approximate by optimizing the elbow. How might I approximate it? Well, I would probably want to choose some family of distributions for q. Maybe I would want to choose Gaussians. So therefore my family of Gaussians is this. The mean, so it's normal distribution with some mean phi 1 and variance phi 2. And then I want to pick phi such that q of z given phi is as close as possible to the distribution in blue. And the red and the yellow Gaussian are two examples of a good fit and a bad fit. Clearly the big green Gaussian is very different from my blue distribution. So that's an example of what would be a bad fit, right? So this blue distribution is much better approximated by the yellow/orange distribution. And when I optimize the elbow over the parameters phi, I will get eventually something that's closer to the orange distribution, which is a good fit to the blue distribution. If I were to start with a set of parameters that is equivalent to the green distribution, and if I perform optimization on that, I will eventually converge to something that's in orange. And now you see that the orange is not exactly like the blue distribution, but it's close enough. So if I draw samples from the orange Gaussian, I will get something which will look reasonably similar to samples that are drawn from the blue distribution. And if I use those samples in my elbow, I will get a reasonably good approximation for the marginal likelihood objective. So that's one example. And I have one other example of latent variable models. You can easily make a latent variable model out of a well, you can easily define a latent variable inference task by removing certain data from your data set. So let's say that we have a data set of digits, but we remove the first half of each digit, and we call that a latent variable. So in our training set, we only see the bottom parts. We never see the red parts. And so all of the top, so X will denote the bottom variables, the bottom pixels, and the top pixels are going to be Z. So now the missing pixels, you can think of them as being latent variables here. I just created a latent variable task out of MNIST. And let's say that we want to fit some autoregressive model over these, over this distribution. So this autoregressive model can parameterize a joint P of X given Z. But again, if we want to compute, if we want to train on this data, we have to find an approximation for P of X. So X bar are the observed pixels. We want to maximize this probability if we follow the principle of maximum likelihood, but we don't have that probability. So we have to sum over all the possible completions in order to compute this objective in its exact form. But if I hide the first two pixels, there's going to be an exponential number of them. There's no way we can do this sum exactly. So we have to use variational inference instead, right? And so what we could do then is to choose. So instead of trying to maximize this intractable objective directly, we could form the elbow. And in order to form the elbow, we need some distribution Q over the missing pixels. Okay, so we need to define some distribution over the missing pixels. And one way in which we could define this distribution is by a fully factored product of Bernoulli variables. So I have, let's say, something like 200 missing pixels here. I define my probability over the top pixels as just the product of 200 Bernoullis. Okay? And the bottom part is fixed. And so what would be now a good Q for the top part? What is the distribution for Q of Z that will set the elbow to be exactly the log likelihood? PZ given X, yes. So the assignment of Q that makes the bound tight, the optimal Q, is the true posterior probability of Z given X. So if I wanted to take a guess at what a good Q could be here, and let's say my probability of X given top and X given, well, first of all, given that I have a probability here, X given top and X given bottom, what is P of Z given X here in this example? It will be putting most of its weight on the correct completion, right? If this model is good, then then probability X top given X bottom should place high weight on the pixels of that digit. So this is a 9, probability of X top given X bottom. If the model is already reasonable, then this should look like the completion of the digit. Okay. So now back to my question, Q of X top given phi. We're going to try to approximate this P of Z, this P of top given bottom using a simpler form, because we're never going to be able to form this distribution with the pixel CNN model. Just it's going to be intractable to represent the P of Z given X. But we can try to approximate it. So what would be a good approximation? I guess if when phi equals 0.5, is that a good approximation or a bad approximation?
Bad.
It's completely random.
Yeah, it's completely random. But we said that a good Q is something which is close to the true P of X top given X bottom. So here the answer is no. What if we set it 1 to be everywhere? So the probability of, no, it's not good. And what if the probability of that pixel is 1? The probability of phi I, the parameter, the Bernoulli parameter phi is close to 1 for pixels that correspond to the top part of the digit Is that a good approximation?
Yes.
Yes, so that will be a good approximation. So when we apply variational inference to this model, we will want to, when we optimize the elbow, we're going to minimize the distance between Q of x top and the true posterior P of x top given x bottom, and the true posterior P of x top given x bottom is something which puts high probability on the true completion. So our Q, the Q that we will learn, will be the third version here, which puts a lot of weight on the true completion. So this is what the variational inference model will learn. Okay, I'm gonna end here, and we're gonna then see in the next lecture how we can use this machinery to not just find a good elbow. Here, so far, we've only optimized over Q to find a good elbow. Now that we have a good elbow, in the next lecture, we're gonna optimize that elbow over P as well, and then we're gonna have an algorithm for learning latent variable models. For now, I'll just quickly summarize the pros and cons. Again, the pros of latent variable models is that they can do latent variable inference. It's fast to sample from them. They're very expressive. But the cons is that they're much more difficult to learn, which is why we had to do all this work, and we're still going to have to do a bit of work in the next lecture.